Chapter 3 is thermal physics, and the first portion of thermal physics is basic thermal concepts. Um, just some definitions of temperature, Kelvin and Celsius scales of temperature. So pretty much go through those definitions with the students because a lot of them might be the first portion of questions in paper 2. Now, the thing that you need to pay most attention to are 3.1.3 and 3.1.4, the concepts of internal energy, temperature, and thermal energy. So, let's start off with internal energy. So, you want to tell them what internal energy is. By the way, internal energy, temperature, and thermal energy are called macroscopic properties. On page, turn to page, yeah. So page 4 tells you that macroscopic property is one that can be observed. So macroscopic properties. So firstly you have internal energy. Okay, what is internal energy? Internal energy is the sum total of the average random kinetic energy of the particles of a gas or solid or liquid. So average random kinetic energy, random kinetic energy. Random, why? Because it refers to the kinetic energy of each of the particles and they're in constant random motion. And a proof of that is via Brownian motion, which shows that all the molecules in a system, in a liquid or a gas, are in constant random motion. So you can tell them about Brownian motion in this part. And also the sum of the potential energy. Now potential energy in a solid, liquid, or a gas is by virtue of its intermolecular bonds, intermolecular forces. Okay, so you want to explain that since intermolecular forces are an attractive force, the stronger the intermolecular forces, the lesser the potential energy. So, for example, in solids, solids have lesser potential energy than liquids, in which the molecules are more freely moving, and liquids have lesser potential energy than gases, where the molecules are further apart. Okay, why is that so? Because in solids, when the bonds are strong, I need to feed in energy in order to break their bonds. So basically, I'm putting in more energy, and then they become liquids. Then I put in more energy, and then they become gases. Okay. Now, the average random kinetic energy of particles. This property, this microscopic concept, relates directly to the macroscopic property of temperature. So, in real life, we cannot actually see the average random Ke of particles. What we can measure is the temperature. And temperature is a direct gauge of the average random Ke of the particles. Okay, so an increase or decrease in temperature simply means that the molecules of a solid, liquid, or gas are moving faster. Alright, why are we talking about average? Because let's say I have a body of 1 kg and I have a body of 5 kgs. They are both at 20 degrees Celsius. Okay. The total kinetic energy of the 5 kg body will obviously be more, the total random Ke will obviously be more than that of the 1 kg body. But the average random Ke of all the particles in the system are equal. Why? Because the macroscopic property, temperature, is the same in both of them. Okay? So you want to talk about that with the students. Alright. The third macroscopic property is thermal energy. Now, thermal energy refers to the transfer of heat via non-mechanical actions between two bodies. So basically the flow of heat from a hot body to a cold body. So it's incorrect to talk about the thermal energy of a particular object, but you'd rather talk about thermal energy in situations where you're talking about heat transfer. The various methods of thermal energy, which you will also discuss, I believe you'll discuss it in this section itself. So the various methods of conduction, convection, and radiation. Okay, these are these are methods of transfer of thermal energy which the students should be familiar with from IGCSE. Okay. Later on, when we move on to ideal gases, you want to remember this chart and let the students know that one of the major assumptions of ideal gases is that there is no potential energy. Why? Because there are no intermolecular forces. Okay. In that case, internal energy therefore becomes a direct indicator of the temperature and vice versa. So that if the temperature increases, internal energy will increase. If the temperature decreases, the internal energy will decrease. Okay. In real gases or solids or liquids, what happens is that we have to take into account the intermolecular forces. Okay. So for example, I could be heating up a block of ice from -5 degrees to 0 degrees Celsius. I am increasing the internal energy and of course the temperature. But at 0 degrees Celsius, I'm still heating it and supplying latent heat, and so therefore I'm increasing the potential energy of the block of ice and the temperature does not increase. So you got to make sure that the student understands this. So that's part 1 of thermal physics. Okay, so the second portion of thermal physics is thermal properties of matter. 3.2.1 is defining specific heat capacity and thermal capacity. So you want to tell the difference between specific heat capacity. So you have Q equals mc delta theta. Okay, this here is the change in temperature. Okay, this is the heat supplied or removed. Okay, or you can say the change in heat or heat supplied rather. Okay. Here you have the mass of object or substance. Okay, and this therefore is the specific heat capacity. Specific heat capacity is therefore defined as the amount of heat required to raise the temperature of an object by 1 degree Celsius for a unit mass of that substance. Okay, so you can see that the specific heat capacity depends, it does not depend on the mass of the object, it does not depend on the temperature change, it simply depends on the type of substance. Okay, so for example, copper would have a specific heat capacity of something, water would have another specific heat capacity. Okay, now this term here, M and C together, that can be also called heat capacity. Now, heat capacity depends not only on the type of substance but also on the mass of the substance. So a smaller quantity of water, for example, 1 liter of water will have lesser heat capacity than 5 liters of water. So you want to make that distinction clear. Okay? So specific heat capacity is defined here.